Tau Ceti is a G-type star like the Sun and just under 12 light-years away. It is a little bit smaller, with about 78% the mass of the Sun, and is half as bright. Tau Ceti is the closest single Sun-like star to the solar system, which makes it a big deal in astronomy. There is a strong possibility of it having a planetary system like ours, and maybe even an Earth twin. Being in our cosmic backyard makes it a prime target for the planned Habitable Worlds Observatory, or HWO. The HWO is NASA's next big budget telescope that will have the ability to directly image Earth-like planets around nearby stars. Its launch is set for sometime in the 2040s, and even if Tau Ceti doesn't harbor any Earth-like planets, the HWO will still be incredibly useful for unraveling its planetary system. Before we dive into what we know about Tau Ceti's planets, there are a few important differences between it and the Sun worth pointing out. To start, Tau Ceti is metal poor. The estimated heavy element content, heavy elements meaning anything heavier than hydrogen and helium, is about 1/3 that of the Sun. This means that planets around this star might have different compositions and formation histories compared to those in the solar system. Tau Ceti is also a slow rotator. A 2023 study found that its rotation period is 46 days, which when combined with a radius of 0.79 suns, means its rotational velocity is about 0.9 kilometers per second. That same work also measured a minimum rotational velocity of 0.1 kilometers per second using spectroscopic data from Express. Since we know the true velocity, this means that Tau Ceti is facing us nearly pole on. Why does this matter? If its planets are aligned with the star's rotation axis, like the solar system planets, then directly imaging them should be easy, since they will never be in front of or behind the star. Over the past couple decades, Tau Ceti has been intensively observed by radial velocity, or RV surveys, in search of planets. How does the RV method work? Spectrographs measure changes in a star's radial, or back and forth, velocity as it and its planet revolve around their center of mass. As the star moves away from us, the light it emits stretches out and becomes redder, and as it moves closer, its spectrum is compressed and becomes bluer. Think of it as a form of the Doppler effect, the same way that a car approaching you sounds louder than a car driving away. By measuring how much the spectrum is shifted red or blue, the star's velocity can be determined, and by measuring changes in its radial velocity over time, one can tease out the signs of an orbiting planet. Tau Ceti has long been considered an RV stable star. In other words, the changes in its radial velocities over time are very minor. The quietness could be due to the star's pole-on orientation. Signals caused by planets will appear much weaker if their orbits are facing us head-on instead of edge-on. Remember, the radial velocity method only measures the back and forth motion of the star, not the up and down or side to side. In spite of this, a team of astronomers led by Mikko Suomi found evidence for 5 planets in 2012. All of them are super-Earths, with minimum masses between 2 and 7 times that of Earth. The inner 3, Tau Ceti B, C, and D, are all closer to Tau Ceti than Mercury is to the Sun. The outer 2, Tau Ceti E and F, have periods of 168 and 642 days. This puts them at the inner and outer edges of the habitable zone. Suomi's work used data from the HARPS, HIRIS, and Euclid spectrographs. The study mainly relied on HARPS since it can measure RVs with sub-meters per second precision. 5 years later, a study by Fabo Feng, Mikko Suomi, and co-workers reanalyzed the HARPS data and found that the inner 3, Tau Ceti B, C, and D, were false positives. Tau Ceti B and C were dismissed as artifacts of noise and stellar rotation, and the evidence for Planet D was lacking. Instead, they found 2 planets with periods of 20 and 49 days, which they named Tau Ceti G and H. Their work also reaffirmed the detection of Tau Ceti E and F. Could there be more planets? A 2020 paper used an algorithm called Dynamite to predict the locations of additional planets. It found that the space between planets E and F could harbor an additional world with a period of 320 days. This places it smack dab in the middle of the habitable zone. Since nothing was detected at that period by previous works, if something does exist there, it could be smaller than the other planets, perhaps even Earth-sized. The dynamite algorithm also predicted another planet between H and E with a period of 90 days, which could correspond to the previously proposed planet D. It's been 8 years since the 2017 study, and Tau Ceti now has a lot more radial velocity data. So far, no one has published a decisive analysis on whether or not these planets are real, but there are some hints in the literature. A 2021 paper by Michael Cretinier and coworkers developed an algorithm called Yarara to clear instrumental noise from the HARPS data. Applying Yarara to Tau Ceti's RVs lowers the significance of planet F's signal, suggesting that it originates from systematic effects and not a planet. A 2022 proposal abstract by the same team noted that their reanalysis of the HARPS data also did not support Tau Ceti E's existence. But what about the other two? I couldn't find anything on planets G and H in the literature. However, there's reason to suspect that Tau Ceti H is a false positive. Its period of 49 days is close to the 46-day rotation period of the star. RV data is often contaminated by stellar activity, especially by star spots that appear and disappear on the surface. As the star rotates and spots come in and out of view, it can create signals that look like planets, but are really not. That leaves Tau Ceti G. Its period of 20 days is not a specific ratio of the star's rotation. The two signals might not be connected, leaving a chance that this planet, and only this planet, is real. With little to go off of in the literature, I decided to do my own analysis of Tau Ceti's RVs. For this, I copied all the data I could find from Euclides, HARPS, HIRES, the APF, Express, and Espresso. This isn't all the data that's out there. There's observations from the Keck Planet Finder, Maroon X, and NIOD spectrographs that aren't publicly available yet. Everyone is looking at Tau Ceti, and it's only a matter of time before an in-depth study of its RVs is published. I could have waited, but I'd rather get a sneak peek for myself. Anyways, I plugged all the data into the DACE server. DACE is free and easy to use, and I have it linked in the description for anyone who wants to try planet hunting for themselves. When all datasets are loaded together, the most significant signal is at 20 days. There are also signals at 361, 980, and 1444 days, which are close to 1, 3, and 4 years, respectively. These are probably yearly instrumental artifacts, and not planets. When I subtract them, the 20-day signal is boosted, and when I subtract that, the most significant signal is at 52 days. This signal is very weak, not to mention close to the star's rotation period. After that, there is no sign of any other planet. The 20-day signal is tiny. Its amplitude is on the order of 38 centimeters per second. Its detection was only possible because of the sheer amount of RV data that the star has. Few other stars have been observed like it. Again, everyone is looking at Tau Ceti. The case for Tau Ceti G being a real planet looks promising, but we can't get excited just yet. There's still a chance its signal is being caused by stellar activity. To get a sense of how stable the signal is, I divided the data into chunks to see how its false alarm probability, or FAP, changes over time. A real planet with a consistent signal should have an FAP that steadily decreases as more data is added. Signals caused by stellar activity often wax and wane, and hardly remain consistent over multiple years. As a sanity check, I also injected a signal with the same properties as the candidate to compare the change in FAP over time. While both FAPs decrease and eventually converge, they do look different. The real signal's FAP falls and then plateaus, while the injected signal drops more consistently. Of course, since planet G's period is between 2/5 and 1/2 of the star's rotation, its amplitude and significance could be impacted by stellar activity. When I accounted for the 52-day rotation artifact, the real and fake planetary signals show more similar changes in FAP with time. This points to Tau Ceti G being a real planet. At this point, I want to emphasize that while promising, it is beyond me to say that Tau Ceti G is a real planet with 100% confidence. An activity-related cause might not be likely, but it's not impossible. Until we have a published analysis examining it in greater depth, its existence remains up in the air. Given that Tau Ceti is already a graveyard of refuted planet candidates, I really wouldn't be surprised if Tau Ceti G joins them. But if it's real, what kind of planet is Tau Ceti G? At minimum, it is 1.36 times more massive than Earth. Its orbit might also be eccentric, kind of like Mercury, but it's hard to say whether the eccentricity is real or an artifact of noise. The true mass is higher, since the planet's orbit is unlikely to be edge-on. Tau Ceti has a debris disk, aligned 35 degrees toward our line of sight. If the planet and disk are aligned, then the true mass would be 2.4 Earth masses. But if Tau Ceti G's orbit is aligned with its star's rotation axis, just like the planets in the solar system, its true mass would be 11.2 Earths. That is a wild difference. Rather than being a rocky planet, it might look more like Neptune. Both the stellar and debris disk inclinations are weakly constrained, so for now the planet's true mass will be a toss-up. A close-in Neptune analog is interesting in its own right. This planet could not have formed close to the star, like the solar system's rocky planets, because there probably wasn't enough material. Remember, Tau Ceti is really metal poor. Instead, it probably formed beyond the ice line, where there was more material in the form of ice. The cores of the gas giants, Jupiter, Saturn, formed in a similar environment. But this planet couldn't grow big enough and fast enough to undergo runaway gas accretion, and instead migrated inwards. Given what we know, could there be other planets? The current radial velocity data show no other significant signals, so any other planets must be too small or orbit too far to be detected. If Tau Ceti has rocky planets, they might be sub-Earths, comparable in size to the Moon or Mars. These kinds of planets have been detected around the stars Kepler 444 and Kepler 37, both of which are metal poor and weigh in at just under 80% of the Sun's mass. Kepler 37 has a sub-neptune with a mass of 5.4 Earths and a period of 40 days that is broadly similar to Tau Ceti G. The two systems might be analogs of each other. What about further out? We know that the star has a debris disk spanning from 6 to 55 AU. If this were placed in our solar system, it would span from just beyond the orbit of Jupiter to the edge of the Kuiper belt. For this disk to remain stable, there cannot be any gas giants to stir it up. That said, the disk is very poorly resolved, so we can't rule out gaps caused by smaller, Neptune-like planets. A 2022 study predicted that the inner edge of this disk might be constrained by a planet about 4 times the mass of Earth, orbiting at 6 AU. Of course, this planet is only hypothetical. And now for the big question. Can we expect Earth twins? Probably not. Assuming that Tau Ceti G is a migrated sub-Neptune, it must have pushed most of the rocky debris out of the habitable zone as it traveled inwards. That would have prevented any Earth-like planets from forming. If there are any planets in the habitable zone, they're most likely sub-Neptunes like Tau Ceti G. It will take many more years of radial velocity data to confirm additional planets. However, future direct imaging surveys could pick up the slack. Even if there are no Earth-like worlds, the HWO will still be useful for imaging far-out planets in the system. Given the ways that Tau Ceti is both similar and different from the Sun, the system will be crucial for testing our theories of planet formation and evolution. That's all for now. While I wish I could give a more conclusive overview, Tau Ceti's planets remain elusive. Hopefully this video goes out of date as new studies are published. I hope you found this interesting, and I'll be back with any updates.